Welcome to the guest lecture on programming with weak synchronization models. So what we're going to do in this lecture is we're going to show you how to do real distributed programs, large-scale, robust, with extremely weak synchronization. So this kind of model will work even on very flaky networks where you cannot give so many guarantees. So the motivation is we want to make it as easy to program as strong consistency and as efficient to execute as weak consistency models. And we will show you a very interesting sweet spot in this space called strong eventual consistency. So the lesson is divided into three parts. So the first part, we're going to show you the basic data structures, convergent data structures, which actually give you replicated implementation needing very weak synchronization. And the data structures we're going to show are called conflict-free replicated data types, CRDTs. And then we'll show two directions where we actually use CRDTs to build real distributed systems. One is LASP, is a programming language and its platform where you can program large applications based on combining CRDTs. And second is Antidote, which is a causal transactional database based on CRDTs. So this lesson is brought to you by three guest lecturers. So myself, Peter Van Rooij from Université Catholique Louvain, my colleague Christopher Mikkeljohn, also from UCL, and my colleague Annette Pionusa from the Technische Universität Kaiserslautern. So this research is done mainly in two European projects, one called SyncFree, which is a seventh framework project that recently completed, and the second one called LightCone, which is a Horizon 2020 project that's just started in 2017. So one of the holy grails of distributed systems is to make them both easy to program and efficient to execute. This is the thing we're going to attack. Now, it's clear that strong consistency models like linearizability are very easy to program. Linearizability is like programming sequential system, but it's inefficient. It requires complex algorithms, which you know very well, such as Paxos and multi-Paxos. The other way to do it, the other extreme, is eventual consistency, where you can have many operations concurrently in the system, and they each will eventually complete. This is much more efficient, but it's hard to program because the operations don't know about each other, and each one doesn't know in which degree of completion are the other ones. So the question is, can we get the best of both worlds? So can we combine the ease of strong consistency with the efficiency of eventual consistency? And this leads to an approach which we've called synchronization-free programming. So how can it work? So to explain it, let me first get back to basics. So a distributed system is a collection of network computing nodes that behaves like one system. So what this means is that there is a consistency model that gives the properties of all the nodes working together. So to make this work, the nodes have to coordinate. They have to send each other messages and run some overall algorithm obeying some well-defined rules, and this is called the synchronization algorithm. So for example, reliable broadcast, which we saw in this course, guarantees an all or none property. All correct nodes will deliver the message, or none will deliver the message. So in the synchronization is the reliable broadcast algorithm, and the consistency model in this case is the all or none property. So how far can we go in this approach? The consistency model has to be as strong as possible, and the synchronization algorithm as weak as possible. So we have a tension between two opposing forces. So what about an extreme case? So it's good to look at extreme cases when we analyze something like this. So the weakest possible synchronization is no synchronization at all. No rules showing how the nodes should coordinate between each other. So there's no consistency enforced. The nodes basically do whatever they want. Now, this is actually extremely hard to program. You have no help at all from the system. So it's clear that we do need some synchronization. How little can we get away with? So a sweet spot is called strong eventual consistency. So this property states that if one has n replicas and they receive the same updates in any order, it doesn't have to be the same order for each replica, then they will have equivalent state. So it's not after each update, but after n updates, same updates received the equivalent state. And the only synchronization we assume is eventual replica-to-replica communication. That means occasionally the replicas succeed in sending messages to each other, which is a very weak synchronization model. So despite the weakness of this model, very weak, it's actually surprisingly powerful. We can define a programming model that resembles functional programming, a concurrent data flow form of functional programming. We can handle non-determinism and non-monotonicity, so it's more powerful than basic functional programming. We can give it an efficient, resilient, distributed implementation. So this is the sweet spot we're going to investigate in this lesson. So in the rest of the lesson, we're going to exploit strong eventual consistency. First of all, we're going to explain how to build these convergent data structures that satisfy this condition. Then we're going to show how to program by combining them. Then we're going to show how to build an actual large database that can do causally consistent transactions on CRDTs. And throughout all this, we're going to give you many applications of this.